Good morning, everyone. So today I have the pleasure to have Professor Giovanni Petri from Northeastern University in London. First, I have to ask a question before the seminar. Is the Northeastern University in the northeast of London as well, or not? But Giovanni works in network science for very long, and he already presented IIS and DEEP about doing topics, so 2 times actually. So thanks for your contribution back then. But finally, he made it physically to Amsterdam. I'm very happy for your efforts to come. And then
any chance of living in London is a good chance, right? Here is particularly nice.
And he'll talk about renormalization, high-order interaction. So the floor is yours. Thanks so much.
And yes, it's the same Northeastern University as Boston. Just we have a campus in London too now. There are actually 13 campuses, like imperialistic university.
But is it northeast of London as well or not?
Yeah. it's kind of northeast. It's like it's Whitechapel. It's like proper EastEnders, just like side of. You get the Tower Bridge, Tower of London, Tower Bridge, then you get St. Catherine's Docks, and just here. So just margin towards Aldgate and Whitechapel, and so on. So yeah, we get students in most of the time because it's cheap enough to live in the eastern, side still, so they actually come into the lab. Anyway, so thank you for the introduction. Thank you for having me here. It's great. I really enjoyed Vita Ballen yesterday and like some unpronounceable beer, which it was very good. So the talk, there are a bunch of names of words in my title here. And I didn't know exactly who was going to be here. So let me start really from the beginning of what I'm thinking about. So when we think about interactions, the typical framework that we're looking at is something where we have some sort of elements within our system, and we have some pairwise interaction. This is basically what we build physics and biology and everything so far. But over the last few years, I started thinking, well, maybe there could be something else, some sort of third-order interaction in which you can have another element of your system that modulates the interaction between the two, or something that is genuinely a third-order interaction in the sense that is at the group level, if you want it with some symmetry. And the idea, for example, this some sort of modulation in an ecological system, the population of trees providing cover for the mice from the eagles, for example. Or like a group interaction where we are all chatting right now. So right now I'm broadcasting really, but if it was a room, it was actually a conversation, it would be something more similar. And in fact, we can sort of look around and shop around for applications from the ecological level all the way down to actual social interactions. And this is sort of, if you want, like the motivation of why we started thinking about this a few years ago. Now, the idea of representing these things goes back to a long time, right? We have a set of languages. Of course, the classic one is the one of networks, which is very powerful. It gives us a lot of statistical mechanisms we can use. But from the point of view, what we need is limited, right? Because the only way in which you can actually describe groups or something that is beyond sort of pairwise interaction is by basically putting in clicks, right? So you cannot really use it. There's a second level of description which you can use, which is the one of simplicial complexes. Now, simplicial complexes are very nice because they give you access to mathematically pretty tools like algebraic topology, persistent homology, and persistent homology, and so on. But it's very rigid because it forces every interaction of a certain order. Whenever you have a third order interaction, you also have to have all the others inside because of the closure of these simplicial complexes. And of course, in this line of representation, you can go all the way up to hypergraphs, which are the most, let's say, versatile, the most flexible, but also with flexibility comes the problem of not knowing exactly what you're doing. In a sense, for example, over there, you have a multiple possible definitions of what a Laplacian operator is, depending on what you're looking at, okay? Again, the idea of looking at groups is not really new. I mean, you can actually go back at least to 87, but probably even more to think about, for example, in this case was Ising, sort of higher order Ising models. But the difference, at least in what has been interesting over the last few years, is that typically you don't have any sort of quantities in the system we're looking at, and the focus is exactly on the complexity that comes from these interaction patterns over here. So the type of equations that for papers you see, look like those. All right. So the equations that were basically social contagion dynamical equations. Now, I was talking about topology and why does topology and why a lot of the conversation has been so far based on topology. Well, that is because it gives us, as I was saying, the possibility of extending our, let's say, dictionary, our toolbox of interaction, right? So if you do network science, you stop here. But then if you start looking at, for example, even just simplified complexes, you start having the possibility of explicitly representing, interactions of that type. Now, and that's, in topology, we call that a simplex, in particular two simplex. And in general, if you have a k-order interaction, you would write it I shouldn't touch that thing, right? Shouldn't touch it. It's going to look like something.
If you can double click again on the slide. Yes. Yeah.
I am so good at this, natural learning. So if you only have this kind of topological description of a higher order interaction of simplices, but something very similar is you must have seen it also when, for example, in multivariate information theory, right? Description in which you're looking at the joint probability distributions of a bunch of variables in your case. Now, all of this is very nice, right? And it's, let's say, in this sense, intrinsically a higher order. The reason why there has been a lot of focus on topological approaches is because when you have something like that, even though all the information is given in here in the set of simplices that you have or in the distributions that you have, it's very hard from a purely statistical description to pick out, to extract the fact that you have a whole, right? Instead, for example, topology gives you that, there is a homological, non-trivial structure in here. So it actually allows you to highlight in a better way, or at least in an easier way, what's something what you could call intrinsically non-local with abuse of notation, let's say, because it really this non-locality appears from the coordination of all these links together. Now, how did people look at this? So why are we discussing this together? And why is, so let's say, higher order interaction funky again, and been funky for a while now? We have to go back, basically. And typically the way you do this, you track these things by looking at reviews that came out, right? So that's a very good track record of who wants to get published and cited a lot. And I'm guilty of this too. And over the last few years, there is a lot of these terms of physics of higher order interactions. But if you actually go back to what happened just before these things, obviously these are some papers that came out by me, but you really have a bunch of these reviews which were focused on describing data from this kind of using lenses that are based in higher order description. And so really, if you want deep down, there are basically two main directions, two main approaches that you can sort of think about, in which you can think about this field. Is one which we could say, we call it from higher order phenomena, yes.
So why do you say that persistent homology intrinsically has something to do with higher order interactions?
Well, because of the language you adopt to describe the data you have. If you in a sense, you are forcing that on the system, right? You have some data points typically in a space, and then you say, well, I'm gonna create a simplified complex out of this. You could create a KNN.
So this is persistent homology on the graph of interactions, not on just the point cloud.
Well, the classic persistent homology is actually a metric space with points in it, and then you have no graph there. You just look at intersections of fat balls of neighborhoods of various radius, varying radius. So that's and the language you use to describe this is simplified complexes, right? So you're basically forcing these lens on the system, on the data that you have, whatever they are.
Is there no interaction there?
No. That's the point, right? That's exactly. Then you understand it as an interaction in some cases, but that's my point, right? If you start from data and you basically describe it this way, you're trying to take out something from the data set that you have, some observable, and you're trying to sort of guess what the mechanisms are.
Okay.
And then the other possibility is that it's the other direction, which is you start for some mechanism where you, for example, write down exactly in equations which you have several terms, and you see, well, how does that what does that predict? What happens? Is there any change, right?
I have a question.
Yes.
Aren't phenomena and mechanism the same thing?
No, the opposite. The way I'm gonna have a slide at that later, so you're gonna see it. But
Okay.
really, for me, mechanism is the equations you write down right now,
Okay,
and then
okay.
and the phenomenon is observables you're inputting. An example of these is, for example, a model that we came out with a long time ago, which is basically a small extension of the classical SIS model of infections, in which you have a node sneezing on another node and infecting it. Okay, so if you assume that you can actually have this kind of group effect where two nodes in a triangle have a different probability of infecting the third node, you end up with a different phase diagram for the system, in which you have the typical continuous transition when you're you don't have a higher order effect when triangles are basically switched off. But when you have these group effects, you end up with a region of bistability. So this is something that you wouldn't really see normally. And this is actually very interesting because if you're thinking about this contagion as a social contagion, because we don't have group sneezing, but we have group, conversation. It means actually that behaviors can change radically if you are in this regime. This is just, you can do the simulation, you can run, you can solve the math here and everything. But the good thing, yes, you can solve everything here analytically. You're looking at me very perplexed.
Solve analytically.
You can write the equation.
Number analytically.
Yes, in the mean field at least. But then there are other people that after that did this in heterogeneous mean field approximations and so on. You can soften the assumptions that we did here because this was a simple complex. And actually down here, other people later basically move this to a hypergraph in which you have a nonlinear kernel, and then they show that there are like a bunch of different phenomena. For example, I don't know if you can see this, but if you perturb a little bit the kernel and the distribution of sizes that you have, you lose the jump, the first order transition, you have some sort of smeared transition. And then this is actually a trace of the fact that you have localization of the infection. So most of the infections, most of the system is fine, but there are some hyperadjacent groups that are very infected, and in that setup were the large ones. So basically, you have this persistence of the infection in the large cases. This is all analytical and numerical, and people have not really done this is actually one of the challenges. Can we actually derive something that can be measured, say, on outbreak curves or something where you can actually see something different, whether you are trying to fit a normal pairwise model, a higher order model, and so on. There is some advancement there, but can I talk about that later? Yeah. Okay. Yes, I'm gonna take it as a yes. Other types of models are synchronization models. Right now, you can imagine of having, the typical Kuramoto model in which you add sort of third order interaction between phases, but you can actually be a bit crazier and put your phase oscillators not on the nodes, but on the triangles, on the edges, and so on, and on. Have what Ginesta calls topological oscillators. And it's fun because then you have all sort of nice decompositions of dynamic, and you end up with phases that you don't really see typically. For example, traveling waves that are not really very common in Kuramoto models, freezing effects of some parts of the system, and other parts keep having this kind of wave behavior. So you have all sort of new phenomena emerging once you sort of generalize the object that you're looking at. And of course, finally, you can also have anti-correlation, some things are going to. And then finally, you have the work that, in a sense, motivated everything from the beginning, which is like when you have coordination of groups, what does it change when I have to coordinate with one person, and then another person, and another person, when it's the 3 or 4 of us together coordinating every interaction. So this is just examples of models that one can think about, okay? At the other extreme, an example is, well, there are many, many examples, and I'm not going to go into the details here. And of course, here I'm blowing my own horn, because, for example, this is work we did a long time ago on fMRI data from people that had placebo or psilocybin. So these guys were high as kites in the fMRI machine. And basically, what we looked at here is a reprojection down to the graph level of the homological structure of the fMRI correlation space. In this case, we looked at it as a weighted network, but really it was just a matrix of the correlations. And then more recently, for example, you can show that using tools of this type, you can do fingerprinting of different tasks with different capacities. So for example, for some tasks, motor and, for example, working memory, you can use, but you better use synergistic descriptions. For other ones, for example, the individual fingerprinting, it's better to use topological descriptions and so on. The interesting thing is that evidence of this kind of topological coding, or at least topological effects are everywhere, from the microscopic level, the level of grid cells, all the way up to global workspace integration, if you want, which is a fancy theory of consciousness that has been proposed recently, and of course is very debated, being about consciousness. Now, let me just, why? One more argument, let's say, guest to the table of discussion of what are these higher order interactions came in very recently from Antoine Allard's collaborators, in which they basically assumed that, so they put forward this idea that really most complex systems that we look at really are low rank, even if you have like a very large network. Down underneath there is an effective low rank structure of these networks. Why is that important? Because what they were showing is that if you do have that, effectively what can happen is that, first of all, since you have a low rank, effective low rank of the network, or hence of the dynamic, any dynamics in the network, you end up living in a low dimensional space, in terms of dynamics. So you have a manifold. But also that means that since you live in a low dimensional manifold with respect to with a very large network that you have, that will induce constraints that we will measure as higher order correlations, dependencies between the variables that we have. Okay, so this is a hypothesis because they show that this is the case on some networks, like structural networks. For example, the network of Facebook, the interaction networks of proteins, and so on. They gave some examples in dynamics where they could follow this, but they didn't really close the loop yet. But this is a very enticing idea. Now, why am I telling you all of this? Well, because if this is the case, then we need to start thinking about what are these interactions that we describe at the mechanism level, and what is the possibility, or what is our capacity of teasing them out from the data, provided they're genuine and they're not induced at this level.
So how precise is this movement along this path? Can you constrain the networks or the dimensionality for which there are only two pairwise interactions, for example? Or
this is a very good question that you should ask Antoine. My guess is that in general, the larger your network, the heterogeneity of the network is going to induce this kind of low rank effect. So you will have some sort of, if you then look at dynamics that you're defining on the original network, but then when you look, so you basically constrain this low dimensional effect. And this is actually not so surprising because some of the recent proposals to, for example, predict dynamics from just time series, instead of trying to reconstruct the network itself, they were estimating some sort of low rank, again, effective surrogate network, and they're using that. And the feeling is that what they're doing is that basically they're taking out they're approximating this.
so there's sort of an original, very big pairwise network on which the dynamics can be captured with sort of effective degrees of freedom that have higher order interaction. That helps out.
And that is exactly the point, right? If you want, for me, the point is that on one level we have mechanisms which could be pairwise or not. On the other level, we have all the behaviors we can think of. This direction is kind of easy because at least we can simulate. The point is that the other direction, and to what degree anything that we see here can actually allow us to say anything about what's happening here, given chosen a scale of description, right? Because then you end up in this kind of who's purest description. Okay, so fMRI mechanism in computational neuroscience at the level of the regions are not pure enough. We should look at the neuropopulation. If the neuropopulations are not good enough, we should look at the single neuron and so on. But given a certain level of description, what is this? Can we do anything with this? Yes.
Question about the previous slide.
This one.
Yes, this one, because in many neural networks,
Yeah.
like theoretical paper, with some even considering the hypergraph structure,
Yeah.
they can always get the low ranks, like even in deep neural network. At the end of the day, they analyze the empirical spectral density. They also find low ranks there. So what in the like high order interactions, I think that can be mapped onto like you need to go beyond the Gaussian distribution. So you need to have the third order, fourth moment order, so on and so forth to capture the correlation between different neurons. So do I really need to map it into this high order interaction, or I just stay with the pairwise interaction, but considering that my variables are correlated in a more complicated way?
You pretty much described the central question of my ERC, which is I don't know. We were trying to figure that. I see what you mean. I think in some cases we can do the mapping exactly, so we know it holds. In other cases, you can always do a low dimensional projection or low rank approximation, and it will work to some degree. But then the question is, does it work because we are sort of squeezing our eyes and we're accepting some error, or does it work because there is something fundamentally true there? And for example, in this paper here, they show that on some RNNs, they can do the derivation, so the reduction exactly, so it works. In other cases, we have other examples. For example, when you look at the phase reduction of oscillators in which you induce observable higher order interaction and so on. But the question is, in some cases, you do know that you have this interaction. How do I tell the difference? So this is, if you want, the whole point of this slide, right? And I don't think anybody really knows. Well, at least I got the money, otherwise, they would have told me no. I think there are a lot of good ideas that are floating in the air, and this is really the right time to think about this. Okay. Now, so this is the general setup. Now, why this is hard, but we basically just said it right now. Why this is so hard in the case of when you assume that there might be higher order interactions, so you want to have them, right? Because in a beautiful world, you would have on the mechanistic side a separation, which you do, and on the observable side, like a nice separation, and everything would match one-on-one, right? But this is not the case, because even low-dimensional models can have non-trivial information theoretic, higher order information theoretic properties, well, non-zero synergy, for example, and vice versa. And so it becomes a mess when you go back. Okay, so that's the general idea. For example, you could talk, like, there's one example of these. This is some work by Marilyn a couple of 3-4 years ago on computational models of of neural dynamics with aging, and you would see that even just by tweaking the structural connectome, just everything pairwise, the synergy and redundancy level, the different orders change, right? You could match the real ones, right? So that there these higher order observables were not explained, or at least could be explained without according to higher order mechanistics description, but you just have it. So on. Okay. Now, what do we like see? A lot of stuff we don't know, but definitely something that we don't know is to do the slightly what we haven't really done is this slightly less hard problem, as I say, which is you actually systematically start with some mechanisms, and then you try and see what you see out in terms of behavior. Then there is another question, which is what is the right scale of reconstruction? Now, suppose you have signals. So imagine that I give you the epidemic curves for every postcode in the whole of the US. Can you reconstruct the network, and can you predict the spreading of that disease throughout the system? And can you do it at what level? If we give you the postcode, can you do it at the postcode level going forward, or should you do it at the city level, and so on? So is there some information that is lost there, and is there a way of choosing this? And that's where the renormalization part comes in. We haven't solved it. We have done one part again, so don't expect this to be close. And then, of course, the next steps in the future will be like drinking this, and this is actually something we're talking about with Fernando. We're trying to do this. So let's start from. Oh yeah, of course, and then hierarchical correlations, which is something else I'd like to not talk about or mention. So if you are interested, you can talk to me about that later. These are two papers that are out there already now. The first one is a PRL that came out 2 weeks ago and so on. The other one is a NatFis that came out in January or something like that. So if you want, there are going to be links later. But let's start. So what do I mean when I say slightly less hard problem? Imagine you have signals defined on the nodes and the edges and so on, and you want to go back to some mechanistic model here. So we have ideas. So we know that this is problematic, and so we can try to do the opposite. We can flip the problem into the easy thing. Specify some models where we do know that there are harder interactions and see what we should expect to see and what not. And so we're going to pick a set of mechanisms, and then study systematically the higher order behaviors that are there. And as mechanism, I'm going to pick up higher order Ising model, which is, you see it here. And by higher order here, we stop at 3 simply because it's easier right at 3. And that's simplicial contagion model I showed you earlier, in which you have infections along the edges, but also along groups, along triangles where you have 2 nodes infected. So you have this extra. And this is the simplest possible case. Now, in terms of observables, we're going to use something that we call total dynamic law information. So you start from O information, which is a mix. It's a difference between the redundancy of a set of variables minus the synergy of the set of variables. If it's negative, synergy dominates. If it's positive, redundancy dominates. We're going to add time by basically adding a target. So you're actually including a future variable, and then we're going to sum on the group. So you're going to have a few variables here and another variable. And so 2 in the present, 1 in the future, and then 2 in the commute. Okay. Doesn't really matter technically. Just imagine this is telling us how much how much information there is in a triplet. If it's positive, you have redundant information about the feature. If it's negative, you have redundant information about synergistic information about the feature. And what are we going to look at? Well, we're going to look at three typical, prototypical parts of our system. I've got this whole simplicial complex with my dynamic defining on top of it. I'm going to look at when I actually have the interaction, the simplest, when I only have the edges, and when I'm looking at just random triplets of nodes that I'm seeing. Okay, so we can run our dynamics, measure this quantity, and just look what happens. Okay, this is the easiest thing you do.
And your variables are binary.
Yes.
Variables.
That's why we did it with this, because you don't have to make choices about optimization. You don't have to do weird Gaussian copula things to compute this thing. We have tried also with oscillators, with phase oscillators, and the results hold, but they flip. So let me tell you, well, at least in the early things we did, they seem to flip. Let me just show you. So this is for the easing model. You start with no higher order interaction, and then you crank it up. And then what you see is that there is the blue bar that goes down, basically. So it means that where you actually have the third order interaction of the triangle, those three nodes become more synergistic, as you would expect. And the same thing happens, it's even stronger in the contagion model, okay? While the other two, for the cliques and for just random triplets, you don't see any changes, okay? So it really means that you are seeing this, you're measuring this excess interaction through the excess synergy. Now, the other cute thing that you can see is that there is, you can measure basically how much of the total, how strong this effect is as a function of how strong the higher order coupling is. And then you see that it shoots up with the easing, but it's actually non-linear and synergistic in the simplicial contagion. While instead, nothing changes for the cliques, right? So, wow, it's even true. Yes. Then my elbow was like a slight touch. What is more interesting is not just that we can see it using a higher order observable, but that we don't see any effect with lower order observables, because otherwise it would be easy, right? So how do we do this? Well, you can measure pairwise transfer entropy on all the pairs of nodes that we looked in the different classes, right? And compare let's say, the differences that we see with the one when we do this with a higher order measurement. So in particular, we're going to look at the statistical distance between the distribution of either transfer entropy, pairwise transfer entropy, or this total dynamical information between the simplices and the cliques, right? And basically, you see that here you don't see nothing when you look at the pairwise. Instead, you see a very strong effect when you look at the higher order. So this is telling you that the presence of the mechanism, and the same thing happens for the simplicial contagion, the presence of this mechanistic interaction is only visible really when you use the right observable, when you do this at the pairwise effect, pairwise level, you don't see it. And then, of course, if you instead look at the triplets versus the cliques, the effects flip, right? You don't have any real signal on the higher order interaction measure, higher order observable, but you have signal on the lower order, okay? Which is actually cute because it means that where you need, at least in this case, you need the right observable to pick up the right synergistic effect, but it's also this effect exists, right? Because you can pick it up.
So what is this measure of statistical distance?
It's a fancy word for the overlap of the distributions.
Is it like a KL divergence?
Yeah, it's not even. They use this because the plot came out prettier because it's defined 0-1, but you could do the KL divergence and the plots would look the same. Okay. This is really the overlap between the distribution. Some weird version of Wasserstein. Now, sorry, I forgot something. Yeah. Oh yeah. And then the other thing you can do is that you can say, well, can we play? Yes, sorry.
What is the version of the model you consider? Is this p-spin?
Yes.
Is it the p-spin?
It's this one.
What is the version?
It's this one. We enforce parity. We actually, so the thing is that you could have a positive effect even if you have like a not positive even number of ups and down. So we only consider what we call, well, Nazi parity, which is all up or all down. That's a positive interaction. That's a positive value. Otherwise, it's a negative percentage. This is the.
So they're 0 or 1 side.
Yes.
And why you don't consider this p-spin model?
Because this was the easiest one we have. You can do it also with the p-spins if you want. Yes.
So why is there a tensor product instead of?
It's the fancy, and it's not that, it's just our way of writing. This is in the paper. It's basically enforcing that parity that I was talking about.
Okay, but it's for a 0, 1 variables, it would be a normal.
Yes, yes. You just of course you do -1, because otherwise the reviewers at PRL get angry. And that would have been an easier way of doing this. Okay, so what you can play with at this point is say, well, is this information enough to construct? And of course, the answer is no. But then you can play an easier game. For example, you can try to play an easier game. Say, for example, I know the network. I know the interaction. I know some pairwise interactions that I have, which is why did we do this? Well, because it was an easy exercise, but also because in some cases it's easier to measure these kind of edges rather than measure the group effects. For example, if you're in an ecological network, you can feed. It's easier to measure feeding rates rather than measure the amount of coverage by oaks to the feeding interaction between eagles and mice. And suppose that you have some idea about how many triangles you should have in your system, right? Just and this is again, it's a strong assumption, but imagine that you can sample locally in your social network how many triangles there are there. So just how many, and if you do that, and then you basically just look at the top, so the strongest synergistic triplets, you can actually you can sort of say, well, I take the top k because I assume there should be those. Even the now approximate number that I have, I can sort of try and reconstruct the system, and you see that as soon as your coupling is sort of large enough, you start doing very well in terms of reconstruction. These are accuracies from the original one. So we started from the simplicial complex, simulated everything, measured the synergy, took the top k, estimated from here, and then very well. And again, you see that there is a nonlinearity in the reconstruction. So altogether, what does this tell us? It tells us that at least in these models in which we do have mechanistic higher order interactions, there is a signature that can be picked up by higher order observables, and that is invisible to low order interactions. Okay, so that's the first plot that I gave you. And then also, since this information is there, it can be, I mean, maybe not perfectly, but it can be leveraged to start trying to do this kind of reconstruction. Okay, you have a question, please.
I do. Yeah, sorry, I wasn't sure if I was going to raise my hand, but you called me. So there are a lot of methods to solve the inverse Ising-Sodlow approximately.
Yeah.
But so this is still a forward problem which you're doing, right?
Yeah.
And so is there no general method to do this approximately for higher asimals with higher order interactions where you fix?
There is no for that, because there you have, I mean, there are models in which you can try to do it, you have, I mean, for example, there was a general one. Well, if you have a general one, yeah. So there have been a lot of the proposals I know, I mean, there is work by, for example, Tiago, Pechon, and so on, in terms of from signals reconstructing network. There has been work on like Robin de l'Abbé looking at, and Yuan Zhao, I think, trying to use basically, how you call it, gradients to reconstruct and so on. Apparently, there is a perfect system that works. Okay. No, and so there are ways, but for example, on the simplicial contagion one, there is, as far as I know, people have are still sort of there. For example, there is some other work by Federico Malizia, Vito Latorre recently, in which they are able to reconstruct even that they know the functional form of the interaction. So if you assume there is a model, then you can do it and so on. So I think there are a lot of effects. There are a lot of bits around, but all of the bits, all of the things that I've seen assume that you have basically perfect data. At least you know exactly. You don't have these spurious effects. I don't know whether we can, and I think that's the next bit. Can we account for these potentially spurious or like emergent higher order effects that you see in the data and figure out whether they come off from the other?
So if I understand correctly, the idea is that to solve the inverse problem, what you can also do is understand the forward problem well enough.
Yes, so they have a good prior, so you get a good prior, yeah.
Okay.
Because I mean, literally, when we started doing this, we were like, well, someone must have done it, and no, nobody done it like directly, just looking at it. So we did it. Yeah.
You are Are you always assuming that you know how your system decomposes into parts? Because you can sort of take products of nodes and can you, maybe the question is that if I take some icing model with some higher order interactions,
Mhm.
I can do a transformation of my spins and then make it lower order.
Right.
Is that possible to do? How do you count the rest?
So I did not think about that in these terms. I do remember from my previous life that at least if, for example, we're doing quantum spin system, you can always find a larger pairwise system a larger system that has a simpler interaction term.
Right.
So you can sort of do this auxiliary construction. I don't know whether I have no idea whether this helps you here. Here we're looking at this in a way that would be closer to what you would do if you had some data. So the idea is that suppose that I have some signals that I've measured either on the nodes or on the edges. What can I do? And if the signals come from something of this type, then it will look like this. And then of course the next bit will be to try and do the opposite effect. So I don't know if you can always do. I'm pretty sure you can probably find a formalism to do that. I don't know if I have no intuition about what it tells you, to be honest. Like for example, every time I saw something like that, for example, in quantum information, it was about simplifying computations, right? It wasn't really about interpreting because the physical problem stayed the same. You just wanted to find a way of coding it better in the computers that you have. So in this case, I don't know. Yep, good. So now, of course, there is a bunch of new things we could do. Continuous models, we tried a little bit. In that case, it seems, for example, at least in the Kuramoto, hierarchical Kuramoto models we looked at, you see the effect seems to flip. So you have more redundancy when you have a hard interaction, at least in the Arena, Scardal simulators in which the phases are still on the nodes. We haven't really tried with the topological oscillators where you have phases on the edges and triangles and so on.
There an intuitive explanation for that? Because I understand that you would get more synergy, that sort of makes intuitive sense.
Yeah.
But why would it get more redundant?
I think because when you have a discrete system like that, you basically, the constraints force you to do, because remember, this is information about the future. So the constraints, they tell you how much information, they tell you better what is going to be the next state of the nodes in your triplet. When you're doing this with the continuous signals, they mix a lot. So I think that you're using the same information a lot because you don't have distinct transition. That's my guess. Okay. But so in a sense, it's like an artifact of how you're measuring this.
Okay. And you're doing it still with OA information.
We tried. We haven't really done it because then we started doing this. There was a master's student thesis in which we got there, and then we were really sure whether we're looking at this properly in the right way. Because how do you decide which copula you use? How you transform this? Is the Gaussian copula changing the data set itself? For example, there are some weird things when you compute all information from the correlation matrix. So it's that's something that I think it's open. At least I don't know I don't know if it's open. I do not know personally if it is open. I would like to see whether if anybody has a solution. For the easy model, we have now the closed form of all these equations. So it's in the applied. For the other one, we don't, as I said. And then, of course, the big problem would be how do we approach this when we just have signals and we are not really sure about what is the underlying model. And so, as we were saying, this is still, let's say, the forward direction. And the next step for us was to be, well, suppose that we do know a little bit more. So we actually start looking at evolution, so I have signals, and then at, let's say, coarse graining of the signals. Can we find a way? Is it possible that the most informative scale in terms of the dynamics is not really the scale at which you measure the signal? For example, you have the signals, the nodes, but it might be some other structure within your system. What do I mean? And so imagine that you have a network and then you renormalize it. Now it doesn't really matter how you normalize it. And then you have a dynamic, some sort of signal or dynamics on the network. As you renormalize the system, you can aggregate your dynamics, the nodes that go in the same macro node. And then you can study how the dynamics changes here, okay? I'm gonna give you the details in a second, but imagine that you have a graph that is sort of modular like this one, okay? You can simulate, in this case, I think it was easy model again. You can look, there is something, you can compute the specific, whatever. Yeah, thanks. I feel a little bit hurt. Yes. You can compute the specific heat of a certain kernel that tells you basically at which level the system is seeing the communities, and then you can decide how you're measuring the information in the amount of information within your system. Right? In this case, just for this example, I'm showing you basically mutual information between a couple of nodes, so on an edge between now and t+1, t and t+1. Okay, and then if you do it at the node level, you end up with some value. But as you coarse grain your system along this renormalization flow, you see that at some point you get a maximum and you stay there. And actually that peak, let's say that plateau, corresponds to when you're actually seeing these communities. What it's telling you is that if you just have the signals and you aggregate the maximum information, at least in terms of the mutual information with the future that you have, is really when you're looking at the nodes, at the community structure. Okay, instead, if you randomize this graph or randomize this graph, you end up with something that looks like this. Same thing. Same thing if you run the dynamics not on the randomization of this, but on the renormalized graph. So the ones that you are getting at each step. So you don't have the economic information, you add it here. And this is, in a sense, it's trivial, right? I mean, it was expected, let's say, because the only feature of this graph is really the communities, right? So the nodes inside are all the same effectively. So they should not have more information about each other. But once you start looking at the different communities, then yes, okay. Of course.
Sorry.
Yeah.
Say that is that the right cross-grain level is decided with the community.
Yeah, I mean, this is in a sense of saying here, if you go back to the example, if I give you all the time series of the outbreaks of everybody in Amsterdam, can you reconstruct the social network? And the answer, let's say, looking at this is no, because what you're going to construct probably is the household level or like your group of, tighter contact group, because effectively you are the same node as all of the others, for example. This would be one possible interpretation. Well, the interpretation of that specific case is that, but this is the kind of message that you get, right? Because there is not enough information in there because everybody's the same, like in a click. There is symmetric. Okay. Now, why am I looking? I'm gonna skip renormalization because you know what it is, and just let me give you how this works. So, why we're looking at this? Well, because you could start from the signals, but if you do have some information about what is the substrate, the structure, you want to use it and see whether that gives you a lens to understand data. Now, the way this was done, the proposal that was done recently is basically to use a diffusion kernel. Basically you plug your Laplacian in here, and so you have this e to the minus tau Laplacian, which gives you a density matrix for every time of this pseudo diffusion on your network. Okay. And then you can sort of threshold that matrix in a smart way to create clusters effectively. Right? So after a certain number of, after a certain pseudo time, so you say, well, all these violet nodes are the same, so they're going to end up in one cluster and in one macro node, and you coarse grain it appropriately, and you do this kind of thing. Now, how do you choose the tau to do the step? It's complicated. It's actually kind of unclear. But really, typically what happens is that you look at the specific heat obtained from the density matrix that you have there, and you basically cut at the first peak that you have, okay? And the idea here is that if you have plateaus across your specific heat, this is when the system itself is scale invariant. So at if you normalize at various levels, it's going to look the same, okay? Now, in the original paper, this was done by comparing degree distributions on, say, power law graphs, which was a little bit tricky because really there is one thing which is invariance of the degree distribution. Another thing is the invariance of the system from the diffusion perspective, which is this thing here, okay? And then the question becomes for us, at least if we want to extend this to systems in which we want to have some higher interaction, is how do we do this, right? So of course you could, do everything. You choose your description of preference. But you can actually say, well, let's start first with the dumb thing. Let's ignore the higher order interaction. I have a simple composite, okay? I ignore the higher order parts and I only use the graph. And for example, if I use the pseudo-fractal simple complex as an example, I just grow this pseudo-fractal. If I renormalize well, then it should basically collapse back on itself, right? And if you do this with a graph Laplacian, just taking into account the edges, you see by eye that it fails, it doesn't work, okay? But this is sort of obvious, right? Because it fails because we are not looking at the right diffusion process, because this simple complex has triangles, so diffusion should be another type of diffusion. And how can we do this? How can we take into account this? Well, for graphs, the picture that you have in your mind is information flowing between nodes through edges, something like this. So you go from K0 simplices through one simplices to other K0 simplices. But if you want to generalize this to any higher order system, then you want to have something that is like from any, so for example, from nodes through triangles to other nodes, or from edges through triangles to other edges, and so on. And so you actually, instead of having one diffusion process, you end up with a family of diffusion processes defined by where your variable live, let's say, where is your origin, the order of your origin simplex, through which, and the order of the simplices to which they are adjacent, right? So what you do is basically from a simplifier complex, you create all these adjacency graphs based on your choice of what is basically your new element, central element, and the definition of adjacency, okay? We're calling this cross-order Laplacian because it crosses orders. Well, and so you have a family of these, and then it becomes cute, right? Because then what you can do is you can say, well, so the coarse grain scheme is the same, right? So the idea is that it's basically the same, but now we're not coloring the nodes anymore. We're coloring the simplices of dimension k, which can be nodes, but it can be edges, triangles, and so on. So do the same game. And I'm not going to get into here because otherwise we're going to lose too much time. This is how we do it exactly. But let's see if it works for the pseudo-fractal, okay? So if you start measuring the specific heats for all these Laplacians, you see that there is one that starts being a little bit flattish down here, okay? And this is the one that corresponds to the 1, 2. So it's like its edges connected by triangles, which is literally the process by which we're building the simplifier, this pseudo-fractal, right? So you're getting the right scale. And also the other one, this one here, is sort of correct because these triangles are touched by edges and so on, okay? So you're getting the right, let's say, attachment kernel of the system. And even by eye, if you do it with the graph, it collapses badly. But if you do it with the right Laplacian, you see, sorry, I stole my own time. There you go. You get it exactly right, at least in this very simple case. Of course, this is a toy model, so we can use something slightly more complicated. I don't know if you're familiar with the network geometry with flavor. These are a family of growing simplifier complexes defined by Ginestra Bianconi and friends, basically, in which you decide you have a dimension, which is what you're attaching. You're touching edges, you're touching triangles, you're touching tetrahedra, and so on. And as you go on, this induces below a certain number of properties, which we don't care about now. But the thing you should really look at is that you see that if you go, as you grow in the order of the system itself that you're building, there is only one good Laplacian that gives you this scaling variance, which we know should be in there because they're constructed in a way to be scaling variance. And it always corresponds to basically the attachment dimension of the model, okay? So this was our way of sort of making sense that it's picking up the right structure. So these lenses, these different lenses, these are all different lenses, are picking up the right structure at the right order in the correct way. Of course, so what, right? Okay, yeah, well, you can also, I can show you that, if we do it wrong, my specific heat starts dying. And if I do it right, my specific heat stays well, right? So it stays correct. And this is because I am renormalizing according to the scaling variant way in structure rather than the wrong structure.
So each of these was constructed so that there's only one Laplacian.
It was not constructed so that. It was constructed by attaching either edges to nodes or edges or triangles through edges or in tetrahedra to faces. So we know that's the protogenerating process.
Right.
We know many beautiful properties of these systems, which we don't care about right now. And we just throw them in, run this thing, and you see that the only one that that thing gets you the right, by right, I mean, the order that is order of the attachment as an object.
What if you mix the iteration process?
We did not do that, and I'm gonna get to that at the end, but I can show you data. So in data, you would have something like that, right? Because of course you would expect that things are not clean, right? And so for example, here we started from, I mean, this is an example on C elegans, which we clicked up. So every click we filled up to a simplex, but it doesn't really matter. So we measure with this, basically we came up with a measure about how long these plateaus are when you have them. And then you can create like a little radar plot of
The data.
this is C elegans, is a network. This is a network which we promoted to a simple complex. We also did it on hypergraphs. Don't
But
worry.
it's their neural network? Or-
Oh yeah, sorry, the C elegant neural network.
Okay.
Yes, sorry. I inferred everybody knew wrongly. And basically what you're seeing here is that the further away, this is like, FIFA players in FIFA 2025, right? So these are your skills. And if you are very away in this direction, it means that you're very invariant on that lens. Okay? And then you can basically play this game and do this for many different networks. And you see that many different systems, really. And then you see that, for example, different domains tend to fall together in terms of the plots that you have. Something else that we can actually do is that since we have, you remember, we had this adjacency graph between order k simplices and through order m simplices, we basically have a graph underlying these Laplacians for every order. So we can randomize those Laplacians, randomize those graphs and create a null model that doesn't know anything about the scaling variance, only knows about the local degree distribution of the variance. And then we measure everything again, and those are the gray lines that you see, okay? And the idea, so the take-home message here is that, for example, in some cases, you have a lot of invariance, but this invariance comes almost completely from just the properties, the statistical properties of the attachment, because your null model is almost the same. In other cases, instead, for example, over here, you have a lot of scaling variance, which is not explained by the statistics of the simplices that you have, and how they're attached, okay? So you can actually play this game, and then you choose your favorite system, and then you do this again.
You don't have to worry too much about that.
No, I know. It's just that I don't know what's coming.
Okay.
I don't really know what's coming either because I changed the slides and I've been earlier and I've been looking at no. Yes.
Do you think of this more abstract contraction in topology combinatorics? It's a combinatorial contraction.
I have thought about that, but why should I think about that in this case? In terms of renormalization, I mean. So, yes, the reason why we did not go deep into that here is because we started, okay, I sort of did a little bit of a Chicago razzle-dazzle thing here. Anybody familiar with what do you think is the standard Laplacian that you should use on simplified complexes? It's a Hodge Laplacian, okay? It's the one that you build from boundary operators and so on and on. Okay. We started from that, and I'm gonna speak about that later in a second. The problem with that Laplacian is a reactive diffusive Laplacian. It's not a diffusive Laplacian, so it breaks everything here. And also it only works for simplified complexes. Instead, the setup we have here works for honestly anything that is higher order, because I showed you graphs that you promote to flag complexes, click complexes. You can do this on hypergraphs. You can do the same thing on cell complexes. Anything works in this case. To do what you're saying, we would need to do it on something that is a topological structure, so we use the Hodge Laplacian, but it's a mess because it's a reactive diffusing. And I'm going to show you some examples later of what I mean by a mess. Okay? But yes, of course, that would be the idea, that you collapse things together. But it's messy when you do it in practice. It's pretty when you do it, when you think about it, but it's not in practice. Good? Okay. So, generalized Laplacian normalization to higher order networks in general. This you can do it on hypergraphs and everything. We were stupid when we did the first version because we wanted to think about simplified complexes. The reviewers brought us to sanity, so we generalized it. I mean, we didn't do anything, we just wrote hypergraphs into simplified complexes. Beautiful thing is that you can actually fingerprint systems using this. It works pretty well. For example, something we're looking at now is can we do the same game on brain data? Right? Can we actually look at either effective or functional hyper networks that you build from this, so on. But the other thing that is important, I think, is that some level of structures can be hidden from the pairwise description. You remember some of those radar plots only had some spike on one higher order direction, not on the others. Okay, and that is important because in a sense echoes what I showed you earlier of the dynamics. In some cases, at the pairwise, if you use pairwise transference, you don't see anything. But if you look at the right higher order quantities, you do see. This is in a sense the structural, not equivalent, but similar things. Now, of course, we're very strict, right? It's Km. We don't have anything that mixes, but it's kind of easy to do it because you can say, well, K that touches through M between M0 and M1, and then you build another location. So this generalizes easily. We didn't really do it because, well, the more you do this, the dirtier the whole writing gets, and you need to have a good idea why you want to do it, what are the scales. So it becomes more problem specific, but you can do it. The other thing that will be important is to assess the quality of these steps, this normalization, according to something that is not defined by the process itself. And I have some thoughts about that, thanks to a very excitable student in EPFL. And then, of course, the next idea would be, well, we're using the Laplacian to do this. Can we think about other operators we could plug in there? Now, Laplacians are super universal. They're the kernel of multiple processes. But what if we put other interaction terms in there, other operators? And we haven't really, I mean, we started a little bit with the Hodge Laplacian, which has all these problems, but we haven't really gone very far there. So I'd be happy to talk to anybody who has ideas there. Then, sorry, let me stop here for a second. Questions, curiosities, well, you asked them already, but anything else? No? Okay, so I managed to shut you up. Well, I was told it was a great success to finish the talk. So this is the official end of the talk. I mean, the rest is like bonus material, so I win. Either by intimidation or by boredom, but I still win. What is the problem with Hodge Laplacian? Okay, so the problem with Hodge Laplacian is this. So now this is that's the very, very, very enthusiastic student. Way too enthusiastic student. Really smart. If you do this with the Hodge Laplacian, there is nothing that prevents you from doing it. You plug it into the operator, into the exponential, go through the pipeline, and then you look at how things get normalized, and then you get in trouble because you see that in the other case, it's basically a hierarchical diffusion. So the set of clusters here gets Gabi, thank you. I'm gonna answer that at the end of it. Somebody reminds me, please. Sorry. So otherwise, I'm gonna lose the train. So not in. Yeah. Thanks, Gabi. Love you, whoever you are. And you see, basically, the clusters in here are not containing the clusters in here, and not containing clusters in here, and so on. Okay. At the end, a little bit, yes, because that's when the diffusion takes over. But this reactive part means that you don't have a hierarchy of partitions. Okay, so it means that you have something normalized now, and then if you're at the next step, you don't know how to normalize it anymore. Right? And you can do it, right? And then you, for example, look at the zigzag homology, what you have in use, and so on. But then it doesn't have the kind of easy interpretation, or at least straightforward interpretation that you have if you have a diffusion process which has a conserved mass and so on. So here, in a sense, the reactive diffusion, and I think I have the details here. Yes, exactly. The point is that, this is the Hodge Laplacian for people who have never seen it. These are boundary operators. Hodge Laplacian is simple complexes. In 2 sentences, is basically telling you that you have 2 possible processes. You go from the simplex at dimension k to dimension k+1 and then down, like a normal random walk, node, edge, node. But you also have the downward. So you go from, say, edge, node, edge. Okay. So, and these are the 2 terms here. Of course, you can write the normal graph Laplacian as just the one defined at the level 0, node, edge, node. Okay, so you go up and down, and you don't have the other part. Problem is that, well, total information is not concerned. This is the non-conservation of mass that I was telling you. But where does that come from? It comes from the fact that you can decompose the Hodge Laplacian using the Weizenberg identity into an actual Laplacian, the Bochner Laplacian, which is signed, which is another problem interpretation. What is a signed Laplacian? How do we play with it? There's people are thinking about this, plus a curvature term. And that's basically your sinks and sources in the system. Okay, so that's what messes up with you. Okay. Great. So we didn't really go forward there, but then we started thinking again, same guy. I don't really want to get into all the details here because he loves Urakawa so much. And so basically everything's about Urakawa. But what we started thinking about, so don't look at this, just talk to me, look at me. So what we started thinking is that, is there a way of measuring what is the quality of a step of this normalization that doesn't really rely on the process that we have itself or some measurement of the specific heat and so on, right? And basically what we came up with, which we are writing right now, is a notion of what we call harmonic degree. So the idea is that you can define harmonic morphisms, which are transformations that push harmonic maps to harmonic maps on from one network to the collapse network to one simple complex to the collapse simple complex. And the interesting thing here is that, and I don't think I have it. No, I don't have it. The beautiful thing is that this is, in a sense, a gauge theory. In a sense, not a gauge theory. It's a theory of invariance, because what it's telling you is that you have an harmonic morphism in this collapse between one system to the next system if the equations that you write for a random walk on this are the same as the ones you write here. In a sense, sort of similar to equitable partition, something that looks like that. Okay. But if you do that, you can then look around every node whether it's locally harmonic or not, and you can measure how good the transformation that you have done, right? For example, here you see the description of, you have the mean and the mean and the median of this process, in which I'm measuring around every node as I renormalize how well I'm doing in terms of this harmonic degree. And you see that if you do the Hodge Laplacian in the right dimension, it kind of works, and then it doesn't really break, and so on. Okay, and this is something that we're trying to propose as a way of assessing any collapse in a structure with respect to a dynamics, which it would be a random walk dynamic, like a unbiased random walk dynamic. Of course, you could think about dynamics. Okay, so finishing up, this is what I said before. Big problem is, how do we really use all this stuff downstream? Okay, and we started, and we were discussing with Fernando yesterday, with some students in Beyond the Edge, the project, Marie Curie network that, I don't know if you're familiar about this, the Marie Curie network that is based here at UVA, the coordinator, Chris Pick, and a bunch of students around. And two of the students are starting to look at basically that renormalization of the dynamics versus the Laplacian in higher order systems. The one that I showed you as a cartoon for graphs, we're doing it for higher order. And then we're trying to see whether at what level of this normalization we can reconstruct better. And the other thing we're discussing with Fernando yesterday was, can we map dynamical renormalization techniques that exist and interpret them under the lens of something where you have the structure? Of course, you need to, this is going to be models again, right? But then the hope is to learn something from models, then we can bring over to cases where we only really have the signals and we don't have real understanding. Okay. With that, this is Beyond the Edge. Sorry, I forgot that I put it here. If you have kids or friends or families, we're going to be publishing a bunch of explainers on network pages, which is actually another locally sourced tutorial pages there. There is a school this summer, if you want to come, in Erice. Beautiful place, amazing little suites, and also Sicilian food at the end of August. And you see that speakers range from computer science, dynamical systems, all the way down to topology, information theory. Maria is going to be there too. Karina is not coming. Probably we're going to have Caterina De Bacco, which is one of the big SBM reconstructions inference people right now. And finally, there is another satellite on this, and that's in June, if you're coming, in Maastricht, so it's close for you. Please come, at least see us, or I don't know if we already closed the submission, but in case, just write to me. It's a very sort of family. I mean, mostly the organizers are Italian, so we're not treating this as a mafia business. and also I am hiring. Actually, that thing up there is not true. Oh yeah, I forgot. This is not true anymore. Literally right now, people are being interviewed for this, second interview for this position at Northeastern. We're going to be hiring postdocs and another student in the next year or so. So if you're interested, get in touch and maybe have a chat and the links there. And these are the faces of all the people that did the work with and for me. Thank you. Yes.
So basically,
Yeah.
your perspective on renormalization is kind of from the graphs. But from machine learning perspective, you can also kind of look at the data, for instance, like a market chain or something, and then do the renormalization there, or more of a data related space go there, and then kind of to preserve also the dynamic information. And is there like a way to reconcile these perspectives, or is there some way that they can?
Well, I think so. I don't have it yet, but I think that's exactly where we want to go. So, for example, I was having conversations about similar ideas in AI safety. Can we actually use ideas from normalization on the data and on the flow, the learning flow, so that we preserve and we mimic, some properties which are desirable for safety? Definitely, there is that. I am not there yet, but definitely I think that is the right direction. This is actually what we're discussing, trying to link the more dynamic based randomization scheme with the structural ones to see whether we can learn something. And in that specific case, I don't know. I should have to think. We indirectly we're looking at actually something. It's actually unrelated. Well, it's unrelated because there is no normalization there, but we're looking at some relearning tasks in mice and in LSTMs as models of mice. And I have a feeling that there is something that is happening in terms of the structure of the weights that stays more modular through this kind of relearn tasks in biological networks that does not happen in normal LSTMs. And that is something where this kind of approaches might sort of shed light on why this is happening. And in the biological part is probably the mice has many things to do, and so it's going to modularize and keep that kind of thing safe. But you could imagine the same argument applying to a LLM that has to do multiple things and be able to keep track of multiple things. Yeah.
Reading again the question from Gabi.
Yes.
How hard is to generalize these methods and observation for continuous process?
It depends what measure. So the information theory parts, well, you have people in the room that are more expert than me at that, and they have problems with continuous dynamics because you don't know how it's harder to measure even usual information if you have continuous signals rather than discrete ones. I think it's very domain specific. For example, there is some evidence that if you have ball signals in from fMRI, you can discretize them enough to maintain. You can discretize and maintain enough of the statistical structure, and thus you could use existing tools. The other bits, I think, generalize pretty quickly. I mean, like the precision homology doesn't really care about where the signals comes from. It just cares about the representation that you have, the weighted simple complexes you build. In the Laplace, in the normalization, well, there are no signals there, so there's no continuous problem. If ever the question is how you extract this, what you call a structure in this case. Is that enough for an answer? Gabi?
But you can have signals in a graph, and then you could normalize those signals as well.
Yes. Okay, I'm gonna steal my own thunder again. So something that we have done very recently, and it works ridiculously well, and we don't really understand well why, is we built signals for edges from fMRI in this case. fMRI on brain. Then you have the structural connector, and then you can have the signal on the nodes. You can build signals for the edges, for example, by basically multiplying the time series together. This is something that is very dirty, but people have done, and you can also do it for triangles and so on and on. What we did in this case was actually different. So we did that, and then we extracted phases via Hilbert transform. And it turns out that if you then do graph higher order topological signal processing, so you decompose the signals on the edges, not using the graph Laplacian, but using the L1 Laplacian, and then you reconstruct. You take the. I always get it wrong. You get the gradient of the decomposition, so not the harmonic part, the gradient part of the signal. That gives you like 99% fingerprinting accuracy on different subjects and task decoding. That was the thing, because we can do very good fingerprinting already with the scaffold, for example, like 99% again, 100% is ridiculously good. I don't know why, but it does, although I have an idea. But we can do task decoding, which is very different, right? Because it's within the same subject, you can actually tell what they're doing. And this is not renormalization on the of the signals, on the edges and so on the graph, but it is telling you that there is information in there that is strongly related to the underlying structure that you're using, because we're using the structural connector to decompose the signal. And so anything that you would then do on the structural component, for example, to renormalize, just carry on, I would expect. Yeah.
So this searching for characteristic scale by looking at this plateau, it reminded me a lot of this new causal emergence work by Eric Howell. It came out like 2 weeks ago. I'm not sure if you've already saw it.
I did not see it.
Okay. Yes. I wanted to ask. So they seem to be sort of.
What do they do? What does he do there?
So they basically also say if you have sort of let's say a Markov process,
Yeah.
a transistor,
Yeah.
DPM, and you can start course grading it, and then looking. So he doesn't look at mutual information about like this time-related mutual information. He looks at what they call like the specificity of the causal. How non-degenerate are the Markov dynamics? And they look for a plateau in this to search for these characteristic fields. And one of the examples that he uses is this idea of like you have a block
Of course.
shape, then you'll find exactly this characteristic.
I think I'm pretty sure they map not one-to-one, but almost, because this is the structural perspective they're doing it on the signal, in the sense that they have the process rather than looking at the structure. Yeah. That would be actually a very good, well, not confirmation, but sort of parallel evidence, and then maybe those things can go together. And if this is done in terms of random walls and Markov chain, it can probably be related to assessed using that harmonic morphism.
Yeah, he does do it with random walks and saying it's just.
Okay, can give me the paper later. Well, I'll look for the paper later.
One question more in a broad scheme like you.
Why?
A scheme that you get high order structures and you want to find the best cost grain of those structures that shows scaling variance.
Mm-hmm.
Did you check whether the scaling variance you find under this procedure relates or not with the pairwise methods on finding scaling variance? Like this
Okay, there are a bunch of questions there. So first of all, I don't assume that the best scale necessarily is correlated to scaling variance. For example, in the community, in the stochastic block model system, the scale is not, there is no scaling variance. There is only the scale of the communities, and that's the right scale where the most information is. So that's one part. And the second part?
Sorry, if there is such scale, you come into a procedure that you can cost grain following the plateau of Laplacian, and that would give you scaling variance if that's what you find.
Yes.
So that how this relates to other forms of finding scaling variance? Do you ask that way? You have a guess.
Which other forms of scaling variance? I mean, other renormalization schemes?
Yeah, other renormalization schemes.
Well, the other renormalization schemes, so the only one that I have, so for graphs, let's stay on networks. So they are the existing ones, they always had this problem, for example, with box counting base and so on, that they were not taking into account the heterogeneity of the structure inside, right? So the reason why the graph, not our work, but the one before, was nice was because it was basically delegating all of that to this Laplacian operator that goes into your diffusion. And so you let the diffusion take care of that for you. And so you assume, so you look at the network from the perspective of something that is moving on the network rather than as describing the structure of the network. So I think that's the big difference, right? And that's why you can play this game of thinking about plugging in different dynamics, right? Because you do that, okay? There is one proposal by Carla Skelly, which is super complicated. It's like scaling variance partitions on all the possible networks, and it's very, well, it's complicated, it's elegant. I did not understand what it's important for. And I don't have an answer to that. I still have to talk to Diego and figure out what the hell is useful that he uses that for. Other schemes are you thinking about?
Like the normal Laplacian normalization without being high order, for instance, the Tommaso.
Yeah, but that's what we built it on. I mean, like Tommaso's, so they proposed the Laplacian renormalization for the graphs, and then we generalized it to the higher order case, and then we, did everything else. But that's basically the same scheme. You're just like lifting it up. So my comment is it's the same in a sense.
Oh, okay, then like, improve the question. So of the exponents you can find in the classic schemes change when you do the high order scheme. Like,
I don't know. We should do that. We didn't think about that. Yeah. Do you want to do it? Let's collaborate. I give you the code, you do it, and then you tell me.
and I'll try to find time. Yeah. Nice. More questions?
No?
Okay, thanks for running again.
Thank you.